Hi, I'm going to present a very brief overview of some of the initial results we've got in trying to use traffic engineering information to improve the performance of OSPF and ISIS networks. So this talk is very similar in flavor to the previous talk, but instead of doing comparisons between vanilla OSPF and the theoretical optimal, our goal was to see if we can tweak the current OSPF and ISIS network protocols to improve their performance. This work is done in joint collaboration with Roch Guerin from UPenn and Christophe Diot from Sprint Labs. So, okay, the initial motivation is obvious and it's already been previously mentioned in just the previous talk. Traffic engineering has the potential to improve the performance of the network. So what we are specifically interested in is, can traffic engineering be used in the current existing OSPF and ISIS protocols? So specifically, we're going to look at three questions. First question being, how much performance can we actually get out of them by using traffic engineering? The second being, how much configuration overhead is required to get this performance out of them? And hopefully these two should be able to put at least an initial footing into answering the question, do we really need to migrate to a new technology just to get performance? So the question becomes, why focus on OSPF and ISIS? Why not just get a new protocol? And the answer is simple and obvious. There is a large established base of OSPF and ISIS running in today's internet. So the technologies are time-tested. People have a lot of experience in using them. So if we were to tweak and make some changes in OSPF and ISIS, I believe it would be far smoother to do than to shift to a new protocol. This also means that we get to save a lot in terms of upgrades of equipment, in terms of training, etc. Having said that, there are some disadvantages of using OSPF and ISIS. One of them is the fact that they're constrained to do shortest path routing, and the other, as mentioned previously, is that they have very limited load balancing abilities. So the only way they can do load balancing is to split traffic equally over all the equal cost paths. And these two constraints might interfere with using traffic engineering to improve performance. So the question we want to ask is, are these two really constraints in the sense that is it actually the case that we cannot get good performance out of OSPF and ISIS? Okay, so the first such work which tried to answer this question appeared in Infocom 2000 by Forts and Thorap. What they basically showed was that if you have knowledge of the traffic entering the network, then it is possible to pick IGP link weights such that you get very good performance. In fact, they gave a very simple local search heuristic and showed that for a large range of topologies, it is possible to get pretty close to the optimal. If not the optimal, at least you can get dramatic performance improvement. But they also showed that there do exist, again, a large set of topologies and traffic matrices where OSPF and ISIS can be really bad and really far from the optimals. And the main culprit they identified behind this poor performance was the limited load balancing abilities that are present in OSPF and ISIS. The next piece of work appeared in Infocom 2001 by Wang, and Zhang. And they basically showed that given any optimal routing, you can match it with shortest path routing. And they did it by using a linear multi-commodity flow problem formulation. I won't go into it, but the upshot was that shortest path routing is not a limitation. If all you're doing is shortest path routing, you can still match optimal routing. But there is something still missing. So the critical piece that was missing in the linear program formulation that I just mentioned previously was the constraint of equal splitting. And this is precisely the same constraint which tripped the Forts and Thorap heuristic and results in poor performance sometimes. What the Wang, and Zhang linear program formulation assumes is that you may be forwarding traffic on shortest paths, but you're not constrained to splitting traffic equally over all these shortest paths. You can split traffic in any arbitrary fashion. So this is clearly a violation of the forwarding paradigm that is right now there in OSPF and ISIS and needs to be resolved. So one of the solutions could be, let's do brute force. Let's go into all these routers and change the hash functions and change the way they split traffic and allow for arbitrary allocation. This is obviously not feasible because one of the reasons is you'll have to go and play with the data path. So what we have done is we have proposed an alternate method which is far simpler to implement, and it hinges on the fact that current day routers have hundreds and thousands of routing table prefixes. Our idea is very simple. The key idea is that what standard OSPF does is that for a given destination, if there are a number of equal cost next hops, it assigns all these equal cost next hops to every routing prefix going to that destination. So what we do is that instead of assigning all the equal cost next hops, we assign only a small subset of the equal cost next hops to each routing prefix. So traffic still gets split equally over these equal cost next hops, but by suitably changing the subset for each routing prefix, we now have a better handle in trying to control how the load is balanced across these multiple links. So the obvious advantage is that we don't have to tinker with the data path. And another advantage is that if you have a lot of routing prefixes, it is possible that you might be getting better flexibility in load balancing. So I'll just illustrate what I said previously. It turns out that this problem is NP hard, in that trying to decide which subset of next hops you want to split traffic equally, it's not an easy problem. However, we have been able to come up with 3 heuristics, which are pretty efficient, and actually for one of them we have a logarithmic performance bound. As I'll show you shortly, they perform really well. The reason they really perform well is because, as I mentioned, nowadays routers have a huge number of prefixes. The larger the number of prefixes, by playing around with the next hops of these prefixes, you have a better handle on the flexibility in load balancing. And finally, the most important change, according to us at least, is that this doesn't require any major changes in the protocol itself. All you go is, you go into the router, look at the forwarding base of each prefix, and remove some of the next hops. In a sense, you're decreasing the size of the forwarding table. And I'll just show you an example to show you how well it works. So this is just a small sample topology of this part of the Sprint ISP backbone over which we ran some of our experiments. And this is just one of the results. So on the x-axis, you have the traffic entering the network. On the y-axis, you have just an arbitrary cost function that we picked up. So essentially, you just see 2 lines. One is this dotted line, which is the force interrupt heuristic. And the other line actually consists of 4 lines, our 3 heuristics and the optimal routing. So essentially, our 3 heuristics are indistinguishable from the optimal routing. The next slide actually better clarifies this. Again, on the x-axis, you have the total traffic. On the y-axis, you have the percentage deviation of our heuristics from the optimal. You can see all other than 0.5%. We have done a number of other experiments, and in all these experiments, we obtained similar results. Okay, so we have come up with heuristics which seem to work reasonably well. So the next task was to see how easy is it to implement. To configure the set of next hops for each routing prefix is clearly not feasible. So what we thought to do was to use an idea that has been often mentioned, as in fact mentioned in the previous talk today, that a large amount of the traffic entering the network is focused on a small set of prefixes. So our goal is that we take care of configuring the set of next hops only for these set of dominant prefixes, and let OSPF and ISIs just fall back to default behavior for the remaining prefixes. And then the question arises, how much overhead by how much is the overhead reduced, and is there a fair trade-off with the performance we gain? Again, the answer we got was in the affirmative, and I'll show you with a small example. So the first column in the table represents the number of routes for which we carefully configured the set of next hops. For all the other routes, OSPF just by default computed the set of next hops, and we didn't touch those. The second column shows the percentage of routes that these dominant set of routes actually constitute. And the third column shows how much traffic was accounted for by these dominant set of routes. So you can see at the second last row that with just 7% of the routes, we are able to account for 75% of the traffic. And in the last row, with around 14 to 15% of the routes, we are able to account for up to 90% of the traffic. So that is also reflected in this second graph. Again, it's a similar graph. On the x-axis, you have the traffic. On the y-axis, you have an arbitrary cost function. So what is of interest are these last 3 lines. So this is the optimal, the strict line. And the 2 dotted lines are with 75% of the traffic and 90% of the traffic. So with just a few tens of percents of configuration overhead, we are able to come reasonably close to the optimal. And again, this is a trend which you have seen in a lot of experiments. Okay, so I'll just quickly conclude. We have been able to come up with a set of reasonably simple heuristics, which in our perception dramatically improves the load balancing ability of both OSPF and ISIs. Well, the main advantage is that it doesn't require any major tweaking. You don't need to change the data path anyway. You just require a small change in the control path. Our results seem to show that these heuristics perform really well. But there are a few caveats. One of them has to do with the heuristics, in that implementing them requires traffic information, the granularity of the prefixes. And finally, there are two more serious caveats, and I think both were mentioned in the previous talk. One of them is, how will the OSPF and ISIS respond to link failures? Or in other words, is it possible to come up with a robust set of link weights which will perform equally well under all scenarios? Or if that's not possible, then to just change a few link weights and still get really good performance. So initial work has again been done by Forts and Thorap towards this end, but the results have basically been that you need a computationally expensive algorithm to achieve this. So we're trying to look at algorithms which are faster and more general. And the second has to do with traffic fluctuations. As traffic fluctuates, the set of dominating prefixes may change, which might require rerouting on our part. So again, the question arises, how much configuration overhead is involved in rerouting, and is the performance that you get worth it? So these are basically the two questions that we're trying to look at. Thank you. Any questions?
I have one for you. How many various topologies did you actually run in your scenario?
Right now we have around 8 to 10 topologies. One of them is based on the actual sprint topology, and the others have been artificially generated.
Are these topologies complex, or are they pretty much adaptive to normal commercial topologies?
We actually use the Georgia Tech topology generator and the Bright topology generator, so these seem to be reasonably well accepted for generating topologies. So I would say that we're not too worried about extreme topologies in our case.
So, why did you rule out the option of just simply taking the best paths that the IGP has calculated and assigning different forwarding weights to them? It seems to me that implementation-wise and configuration-wise, it would have been the simplest approach, and unless I'm mistaken, that is probably it is functionality already present in most major vendor implementations.
I'm sorry, I didn't quite get the question.
So you have multiple paths.
Mm-hmm.
Instead of trying to calculate for which prefixes to remove part of a path, why don't you just say, well, these multipaths 10, 80% always for all prefixes that resolve over this IGP round? Why did you rule out that approach?
Essentially, you're saying that essentially saying that we should try to spread the prefixes such that 20% of them are on one link and 80% on the other link. Is that what you're saying?
Exactly. That's what you're trying to achieve. But
that's essentially what we do. In that we look at the prefixes and the traffic arriving in them, and then we decide over which next hops to place each prefix. So what I was saying was just a more general case. In that, I could allocate and say that some of these prefixes go only on this next hop, some of them go only on this next hop, and some of them may go on both next hops.
I understand you use that to get the percentage of traffic division, but it seems to me that you're creating a very complex method while you could have configured the next hops to have weights. I mean, I don't know if you're familiar with Cisco's EIGRP, for instance. It allows you to set weights on your forwarding next hops.
I'm not familiar with that technique, but that would definitely be an option, I guess.
Was there any degradation in results for like a large gap in the dimensions of the network or the topologies, in that you had like OC3s and maybe OC182s in the same region, or something to that effect?
No, we didn't specifically look at OC3s, OC12s. We randomly simulated link capacities over a wide range, and we also randomly simulated intensities of prefixes over a wide range, but we didn't find any degradation.
Okay, so the dimensions of the network were not considered.
The dimensions we did look at up to say 100 node networks.
Okay.
And we haven't looked farther than that yet, but we haven't found any degradation yet.
This is just a comment, actually.
Just so I can inform everyone, this is the last question on this topic.
There's just a quick comment on the response to traffic fluctuations. There's actually work done at Sprint Labs itself, which is somewhat encouraging in this direction, because that work demonstrates that the elephant and mice phenomenon actually follows a diurnal pattern. So the elephants tend to remain elephants and the mice tend to remain mice, which would actually help at least partially answer the traffic fluctuations issue for you.
Yeah, that's quite true. I think the previous talk did mention this.
Yeah, and indeed there's work done at Sprint Labs, which I don't know if you're aware of, by Supratik and company, that addresses at least partially this question. So you might want to look at that.
Okay.
Thank you very much.